Hello friends, we already saw the introduction of the subject radiation and microwave technique. Now today we will start the unit number 1, that is the fundamental theory of radiation and radiating element. Now today's topic is the fundamental equation for free space equations over there. Now the content of unit number 1 are like that: fundamental equations for free space propagation, Friis transmission equation, definition of antenna, radiation mechanism and types of antenna, performance parameters such as radiation pattern, directivity, gain, efficiency, half power beamwidth, bandwidth, polarization, input impedance, radiation efficiency, effective length, effective area, radiation sphere. The reference books are number 1, C.A. Balnis, Antenna Theory, Analysis and Design, John Ville publication. Another book is that K.D. Prasad, Antenna and Wave Propagation, Satya Prakashan, New Delhi. Now basically, what is meant by the radiation? Radiation is nothing but the emission of energy as electromagnetic waves. Whenever the EM waves are radiated in both the direction from the dipole, then it will be propagated in a free space as a part of a electromagnetic energy. Now prerequisites required for this subject: electric field intensity E, magnetic field intensity H, electric flux density D, and magnetic flux density B. The relation between these all components are electric flux density is equal to epsilon into electric field intensity. Magnetic flux density is equal to mu into magnetic field intensity, and J is equal to rho, conductivity of that with respect to the electric field. Now here the Maxwell's equation in static conditions we can observe. There are 4 different Maxwell equations available. So the Faraday's laws tell us that the electric field, circulation of electric field is equal to the negative rate of change of the flux of the magnetic field. Ampere law tells us that the circulation of magnetic field is equal to the surface integral of the both conduction current J and the time varying displacement current. Gauss law electric field can be mentioned over there, that volume charge density is identical to the divergence of the electric flux density, and Gauss law magnetic tells us that no isolated magnetic charge exists and it will be that is the magnetic flux line close upon themselves. So these are the time varying Maxwell's equations. Now in general we are mentioned the vector A is equal to real component of the AS into the complex term e raised to j omega t. If we differentiate with respect to time, then we get it a time variation of the vector A, which is equivalent to the multiplying phasor component j omega. So this is the time varying component we get it over there if we differentiate with respect to t, and that's why similarly the particular electric flux density as well as the magnetic flux density also we can observe, where this is the time variation vector component we are getting one over there. So these are the Maxwell's equation again. Now the fundamental equation of free space, using the vector quantity we are just multiplying curl of A bar, so that gives us the equation curl of dot A bar minus curl square A. Maxwell's equation curl of E bar is equal to minus j omega mu h bar. If you taking curl both sides, then we get it a minus, finally minus equation minus j omega mu rho plus j omega epsilon E bar. Now these are the modifications takes place in equation, and we get a final equation over there. Curl square E bar is equal to gamma square E bar, and curl square H bar is equal to gamma square H bar. These are the wave equation or the Helmholtz equation we get it over there. Now here the assumption is that always be whenever the signal is propagated in XYZ direction 3 dimension, so the Z is the direction of propagation, and that's why wave in a TEM mode also, and the field is constant uniform in the plane perpendicular to the direction of the propagation. So the final equation is that E of X is equal to E of X S0 e raised to minus alpha Z cos of omega t minus beta Z, where E of X is the instantaneous form, alpha is the attenuation, beta is the direction of propagation, and t is the time constant we get it. This is the three-dimensional EM wave which is propagating one in a particular direction. The particular fields are available in a X and Z direction. Now without the loss of generality, if you assume that the wave propagate along the AZ and that of E of S has only the X component, then E of S bar is equal to E of XS Z A of X cap. Therefore above wave equation becomes del square minus gamma square E of X Z is equal to 0, and the final scalar equation we get it in a linear homogeneous differential equation part. Now here if we compare the gamma value is equal to general equation alpha plus j beta, alpha is the attenuation and beta is the phase constant, and another equation gamma is equal to under root of j omega mu in a bracket sigma plus j omega epsilon. If you compare this equation and compare the real part and imaginary part, then we get it the alpha equations over there as well as the beta equation over there, where the alpha is known as the attenuation constant or attenuation factor of the medium. It is measured of the spatial rate of decay of the wave in the medium, measured in Nepper per meter in decimals per meter over there. Finally we get it the H is equal to under root of j omega m upon S plus j omega E, where U is equal to omega upon beta value. So these are the components. Now free space equation. Now free space is the space that has the following characteristics. Number one, it doesn't interfere with the normal radiation and the propagation of the radio waves. It has no magnetic fields, it has no solid bodies, and it has no ionized particle. But the free space doesn't exist anywhere. However, the propagation of wave can be very easily explained in a free space, and that's why here we need to observe the specific component here there. So sigma is equal to 0, epsilon is equal to epsilon 0, mu is equal to mu 0. Using these values, as it is a free space, there is no attenuation takes place, so alpha is equal to 0. Beta is nothing but the omega upon c, and u is nothing but the velocity of light actually c. So this one beta is changing one with respect to the wavelength. Lambda is equal to 2 pi upon beta, and this is the propagation takes place. Eta 0 is equal to under root of mu 0 upon epsilon 0, which is normally called as the intrinsic impedance of the free space medium. Now Friis transmission equation, in that we can see that this is the transmitting antenna and this is the receiving antenna, where all components are available for the transmitting antenna and receiving antenna, and transmitting and receiving antenna are separated by the distance r. So these are the transmitted power, transmitting gain, directivity of the transmitting antenna, then the efficiency, then the reflection coefficient, and this is the rho t component we are getting one over there. So if you try to calculate the power radiated by the transmitter isotropic manner, so it can be written as a transmitted power upon the distance covered, Pt upon 4 pi r square. transmitting antenna having some gain, so it will be multiplied with the above equation. So the transmitted power density in the direction of main lobe is the Pt Gt upon 4 pi r square, where the power intercepted by the receiving antenna with some aperture area of the receiving antenna. So it is the Wt into Ae, that is called as the received power. So that can be calculated as equal to Pt Gt Ae upon 4 pi r square. Now the maximum directive gain and effective area are related with the aperture of that. So gain is equal to 4 pi upon lambda square Ae, or Ae upon G is equal to lambda square upon 4 pi. Whereas if you put all these values in above equations, so we get it the final equation of received power is equal to transmitted power Pt into transmitting antenna gain Gt upon 4 pi r square, distance between transmitter and receiver, into G of R, that is the receiving antenna gain, in a bracket lambda square upon 4 pi. So here there is a final equation which is most important equation for solving the problem. But here the lambda square upon 4 pi, if we invert it, so it is a negative component we are getting one. That is what we call it as a path loss of the particular component. It is called as a spatial attenuation factor. Electric field at the receiving antenna. So these are the radiation intensity Wt is equal to E into H, eta intrinsic impedance is equal to E by H. The modification of this equation is Wt is equal to E square upon eta, where eta is 120 pi. So we can calculate E is equal to Wt into eta value. We are putting the value of Wt, Gt, Pt upon 4 pi r square into 120 pi. And that's why the final equation is modified like that. E is equal to under root of 30 Gt Pt upon r. So this is the field strain at the receiving antenna at a distance r for the free space conditions. Thank you very much.